In this video, we will use stoichiometry to determine how much product or how much reactant we need using the balanced chemical equation. So an example problem that exploits stoichiometry is this problem here. So pure oxygen is made by heating mercury 2 oxide. Okay, notice the Roman numerals by mercury because it's a transition metal. And the first thing here is to balance this equation. So we can do our inventory here. This seems pretty straightforward to me, just by glance. We have one Hg, and then we have 2 oxygen here. We have 1 oxygen here, so if I put a 2HgO, that means I'll have 2 Hg and 2 O. My oxygens are balanced, and I can balance out the mercury Hg by putting a 2 here. So probably the most easiest equation that we can ever balance. All right, so that's our answer to this equation here. Just double check 2 in front of the Hg reactant side, 2 Hg product side, 2 oxygen on the reactant side, 2 oxygen on the product side. Yes, we are balanced. Okay, this question here in part B is asking how many grams of mercury and how many grams of oxygen are formed from 45.5 grams of mercury 2 oxide, HgO. Again, we can utilize the balanced chemical equation to determine how much grams of these two products will be made. This is, again, another definition of the mole. The coefficients of the balanced chemical equation can give you a definition of the mole. So always start with what you're given, 45.5 grams of HgO, and let's go ahead and convert it to moles. 45.5 grams of HgO, 1 mole of HgO has about 216.6 grams of HgO. I'm getting that by adding the weights of Hg, which is 200.59, and then oxygen about 16.01. Adding those together, I'm getting 216.6. So we are given, I'll highlight this in blue, we're given that. What are we being tasked to find? We're being tasked to find grams of mercury. So I'll highlight this in yellow. So what's the relationship between grams of mercury and grams of HgO? Well, it is a 2-to-2 ratio. That is obtained from the balanced chemical equation. So for every 2 moles of HgO, there is 2 moles of Hg. So let's go ahead and put that in as our conversion factor. Again, this is where the definition of the mole comes in. Coefficients of the balanced chemical equation gives us the mole-mole relationship only if the equation is balanced. All right, so now we've got that relationship stemming from our equation. Now it's just a matter of converting the moles of Hg to grams of Hg, and we already know that for every 1 mole of Hg, we have 200.59 grams of Hg. So again, common theme in this course, always cancel out your units. This gives you some clarity and a little bit of validation that you are getting the right answer to the question, or at least the direction of which you're going to the problem is correct. You're not going offsetting direction or any tangents, provided that your relationships with the mole are correct. That's why it's essential to know those 4 definitions of the mole. See here the grams and grams of HgO cancel. The moles of HgO cancel with the moles of HgO. The moles of Hg cancel out with the moles of Hg mercury. We are left with grams of mercury, and that is what the problem is asking us to find. So let's do this in our calculator. 45.5 times 2 times 200.59. Take that product divided by parentheses 216.6 times 2. Close the parentheses on your calculator, hit the equal sign, and let's see what we get. So doing that, I'm getting 42.14 grams of mercury. Definitely want to check my work in case I make a calculator error. You can generate 42.14 grams of mercury. Well, how many grams of oxygen can we generate? So let's highlight this in a different color. Let's highlight this in purple. And we're going to do the exact same thing. Start with your starting material, and then use the mole-mole relationship from the balanced chemical equation. So let's go ahead and draw that stoichiometric relationship. I went ahead and ran through the whole train here. We're given 45.5 grams of mercury oxide. Essentially, we want to convert it to moles. That's always a good premonition when you start these problems. And then use the mole-mole relationship. So for every 2 moles of HgO, okay, we have 1 mole of O2, and that's shown here. And we know that for every 1 mole of O2, there's 32.02 grams of O2. So remember, it's not 16. We have 2 atoms of oxygen in O2, so it's going to be 16 times 2, which is about, from your periodic table, 32.02 grams of oxygen. So using that, I'm getting an answer in my calculator, and again, double check my work, of about 3.36 grams of oxygen gas is liberated. Part C is how many grams of HGO would you need to obtain 33.3 grams of O2? Let's highlight first what we're given. So I'll highlight what we're given in the yellow highlighter, and then I'll highlight what we are being asked to compute in a different color. Let's make it green. Okay? So always start with what you're given, 33.3 grams of O2. Good inkling is to convert it to moles and then use the mole-mole relationship from the balanced chemical equation. So let's go ahead and solve this problem. It's worth noting that we're doing this by balancing the chemical equation. You see, if we don't balance the chemical equation, this whole problem will be computationally incorrect. So 33.3 grams of O2 is the starting amount. Let's go ahead and convert it to moles. Which, again, as I mentioned before, is a good way to start off many of these stoichiometric problems. Now we have moles of O2 from, let me repeat, for every 1 mole of O2, 1 O2 here, there is 2 moles of HGO, a 2 here. And the importance of the stoichiometric coefficient cannot be understated. So for every 1 mole of O2, we have 2 moles of HGO, and then for every 1 mole of HGO, we can calculate how many grams of HGO are there, and that is 216.6 grams of HGO, getting the values from the periodic table. All the units cancel out. We're left with grams of HGO. The problem asks us to find the answer in grams of HGO. So doing this on my calculator, again, please check my work, 33.3 times 2 times 216.6. Take that product, divided it by 32.02 grams. My answer is 451 grams of HGO. In order to get 33.3 grams of O2 product, you'll need a starting material of about 451 grams of HGO.